So let me just take a look at who's in the chat right now. Well, there's only one person there. That's okay. I've got some questions that I want to do, and you know, if you have any questions, just put them in the chat, and I'll look over every once in a while and answer them. Okay, so I'm going to try to kill a couple of birds with one stone. There was 3 questions out of all the practice problems I gave you. I gave you the solutions, but I forgot to give you the solutions for 3 practice problems. And so I thought, why don't we do them right now? And I'll do the ones with the same numbers as I have online, but otherwise I could even do variations on them if you want more. But let's start. These are the extra questions for electricity and magnetism. All right, so let me actually switch to, let me get rid of my image so that it's easier to see here. Is that going to work there? Yeah, okay, there we go. All right. Oh, can't seem to. Okay, so just trying to get my whiteboard ready. It's not quite working, but it is now. Okay, it should be working now. Let me just make sure here. Yep, it is. Okay. Technical difficulties there. Okay, well, my first question is basically making a capacitor out of parallel metal plates. And, you know, usually we don't build capacitors, you just buy them. But this is kind of an important question, especially if you're in biology, because cell membranes usually have 2 sides to them, and they act like capacitors. So you can talk about the capacitance of cell tissue, you can talk about the capacitance of any tissue, and you can look up these numbers online. And so it's useful to see how this works. So basically what you have are 2 square metal plates here. Or I guess they're not really metal, but they're rectangular. Metal plates like that. And they're each 10 by 20 centimeters, okay? So this area that goes into the formula for calculating the capacitance of parallel plates is basically the area of any one plate, or the area of the facing plates. Okay, so each plate has this area here, and that's what we'll use right there. Okay, they're held only 1.5 millimeters apart, and that's the distance between them right there in the formula. And the parallel plates, you know, they could just be like, you know, 2 metal plates with no space, with no material in between them, with a vacuum in between. But you could actually put a dielectric material in the middle of them, and that enhances the capacitance, and that's what this K is. And this epsilon naught, that is basically just the permeability of free space. And I better get that ready so I have it when I need that number. No, permittivity, sorry, permittivity of free space. And also known as the vacuum permittivity. Okay, I've got the number ready. So let's go ahead and just substitute in here. This is a really simple problem. There's not much to it, but it is, like I said, insightful. All right, so the K, which is the dielectric constant, is 13.5. It's a dimensionless number. And epsilon naught is, now this has got too many digits, so I'll get rid of a few digits. The units are farads per meter, like that. And I'll leave the units in there so you can see that they work out. But that's too many digits right there. So let's get rid of some of those digits. And let me use the same notation throughout. So there we go. So it's 8.85 times 10 to the exponent negative 12 farads per meter. Okay, and now for the area, okay, and don't make the mistake of doubling this number, because I know there are 2 plates, but it's just the area of one of the plates. But it has to be in meters squared, and this is centimeters and that's centimeters, so we have to convert each one of them to meters. So that's 0.1, 10 centimeters is 0.1, multiplied by 0.2, and that'll give us meters squared, okay, divided by, and the same thing here with the millimeters, all right? So yeah, it's 1.5 millimeters, but we have to convert that to meters, and that means we have to move the decimal over. to there. Okay, so millimeters is 1,000, so move it over decimal over 1, 2, and 3, like that. Okay, and you can see I put the units in here because what you have here is a meter in the denominator there, that's farads per meter, and you have another meter in the denominator there because you're dividing by d. Okay, so you have meter squared in the denominator and meter squared in the numerator, so the meter squared will cancel out, and what you're left with are just farads. Okay, and nothing very deep here, just plug it into my calculator, and I'll give you that number in a second. All right, there's the number. Okay, and sorry, let me just switch over to the, because I'm going to put this up online. I want to make sure I use the same notation throughout. Okay, and that's farads. All right, now on the test, you probably wouldn't see the number reported that way. I expect you to know the metric prefixes, and I'll just mention them very quickly here. Milli is 10 to the minus 3. Okay, micro, and do I have a micro nearby here? Actually, give me 1 second. I'll just pull up a little, the symbol for micro. All right. Copy. Paste it in there. There we go. Okay. That's 10 to the exponent negative 6. Nano is 10 to the exponent negative 9. And every once in a while, with capacitance, you might get even a pico, which is 10 to the minus 12. Okay. So there we go. So this, I would actually report this number as 1.59. Actually, I'd probably round it off. And the 10 to the minus 9, what's that? That's nano, so it'd be nanofarads. Okay, so there's the answer to number 1. All right, easy enough. Okay. All right, let's take a look at number 2. Well, it's actually not. It's actually number 4 in online, but it's the second one I'm going to do right now. So this is when you have a resistor and a capacitor that are in series, and you may optionally have a battery. If you have a battery, then this thing is going to start charging up. Okay. Otherwise, the capacitor will start charging up. Otherwise, if you just have the capacitor and the resistor, then what will happen is you have to prepare the capacitor with some charge, and it'll discharge through the resistor. Okay, and the formulas are different. So the formula I have right here, this one, let me scroll up a bit, that one right there, this is for when you have the battery. Okay, in other words, when it's charging up like that. Okay, I mean, I can give you the one when it's discharging, although we don't need it for this problem, but just for completeness, this is what the equation looks like for discharging. Okay, that's without the battery. All right, so maybe I can just put in here with battery. All right, and this would be without battery. All right, I'm going to put this up online, so I might as well do a good job right now. So this is the one we want because we have a battery, and this thing is going to start charging up. Okay, so it says that when we close the switch, the capacitor begins to charge. Okay, and I didn't say it here, but just to be very clear, it's assumed that the capacitor starts from 0 charge. Okay, what's the maximum charge that will accumulate on the capacitor? So A is what's the maximum charge in this equation here, which is the one we're using. There's some ingredients. Q of t, that's not Q times t, that's Q as a function of time, meaning that Q changes over time. Q is the charge on the capacitor, t of course is time. Okay, this Q naught, that's the maximum, because this piece here starts from 0 and it builds up to 1. Okay, and so 1 times the maximum is the maximum. The maximum actually does not depend on the resistor. What the resistor does is it just kind of slows down the process, but it doesn't ultimately stop it. And the thing that's going to be accumulating the charge is the capacitor, and the capacitor is accumulating the charge because there's a battery pushing on it. Okay, if you wait long enough, there'll be some maximum that the battery would push on there, and it's just this right here. Okay, Q naught is just equal to CV like that. Okay, and in fact, that's just a definition of capacitance right there, because the original, when I first wrote the equation for the capacitance, C is equal to Q over V, that's the definition of capacitance, and that's just a rearranged form of that. Okay, so what do we have here? Well, we have the capacitance. I told you it's 50 microfarads, like that. And we have the battery. I told you it's 20 volts like that. Okay. And we can't quite multiply. Well, I guess we could just multiply. But you know what? Keep that mu aside here like this. A farad times a volt. You go, what's a farad times a volt? Well, that's a coulomb. And 20 times 50 is going to be 1,000. Okay. And so... let me see here. So the 1,000, you know what? Let me. I will change that micro to times 10 to the exponent. Remember what micro is? 10 to the minus 6, like that. Okay. And the farad times a volt, that's going to equal a coulomb. Now 1,000 times 10 to the minus 6 is just going to be 10 to the minus 3, like that. And that's a coulomb. Or you could write this as 1. 10 to the minus 3 is millicoulombs, like that. Okay, so that's the maximum it's going to build up to. It's going to build up to 1 millicoulomb charge. All right. Whoops, why did I do that? There we go. B. All right. So no resistor. Resistor doesn't affect the maximum charge accumulated. Okay. The next one is, what is the charge on the capacitor after 10 seconds? Okay. And to answer that question, actually, implicitly, I guess I could have asked the question before that. What is the characteristic time, or the time constant? And here's the time constant. In order to answer this, what is the charge after time 10 seconds? We actually have to get tau, because tau comes into the equation here. Okay, and so t is a variable. You know, it increases over time, but tau is just a number. And it depends on how big the resistor is, because the bigger the resistor, the longer it's going to take to charge up. And it depends on the capacitor, because the bigger the capacitor, the longer it's going to take to charge up. Okay? And so what's R times C there? Well, R is 300 kiloohms. And C is 15 microfarads. Like that. And let me do this in a couple of steps systematically so you can see how to do this. The K is kilo, which is times 10 to the 3. Okay. And the micro is times 10 to the minus 6, like that. Okay. And so now what do we have? We do that on the next line. We have this. Let me do that on my calculator. Probably could do it in my head. So I'm getting 15. Okay, 15. And what are the units? Well, you've got an ohm times a farad, like that. And you wouldn't think it, but I did show you this when I actually did the recorded the lecture on this material. I actually showed that when you multiply an ohm times a farad, you get seconds. So this is 15 seconds. Okay, which is actually quite a remarkably long time constant. All right. But that's because we have a very large resistor here, and so that large resistor and a large capacitor. So large resistor, large capacitor means it's going to take a long time to fully charge this thing up. So that 15 seconds, that's not the time to charge up. That's just this time that goes in here. And so now you can start to answer questions by just plugging into this equation. How much charge are you going to have after a certain amount of time? So now we can answer part C here, like this. And we'll just take this equation here, like that. And what do I ask? After 10 seconds. So this is going to be the charge at t equals 10 seconds, like that, okay? So now we can substitute in the numbers. For Q naught, what are we going to substitute in? Actually, let me do that on the next line. For Q naught, we're going to substitute in. Well, we have Q naught. There it is. It's 1 microcoulomb. Okay. 1 minus the exponential of, that's Euler's constant. So you may have to figure out how to do that on your calculator. Minus t, so the time is after what, 10 seconds? So minus t is 10 seconds here, divided by tau, which is 15 seconds. Okay, and I'll put in the units here. 10 seconds divided by 15 seconds. The exponent has to be dimensionless, and so you can see that the seconds are going to cancel out. And there you go. So now what? Well, let me do that on my calculator here. So I've got 1 minus e to the exponent negative 10 divided by 15, close brackets, equals, and just change modes here so that it's easier to read. There we go. It's going to equal this. Okay. So it's going to be 1 microcoulomb multiplied by that number there like that. And the answer would then be 0.487 microcoulombs, or I might write that on the test as 487, sorry, millicoulombs. I said micro. Millicoulombs there, millicoulombs there. It will be micro coulombs. Okay, so there we go. That's what it's equal to after 10 seconds. Now I did ask after 20, but I think that's easy enough. I'll let you guys do that. What would you do? You just put 20 in there, okay? And you'll get a number here, and the number here would actually be bigger. Because what? Because it's heading towards 1 microcoulomb. Okay, so you know, this is almost like halfway there. 500 microcoulombs is about half of a millicoulomb. Okay, and so it's heading there, but it isn't there yet. And now let's do part D. Now part D is only appropriate for the for calc students. I don't think there's any physics 112 in there, but if there are, this is not for the physics 112s. Let me just see here if there's any questions in the chat. Nope. All right. So how would you do this? So let's read it. So what is the current through the resistor after 10 seconds? And you go, geez, how do I get that? Because if you take a look at this equation here, there's nothing about current in there, is there? Okay. But current is equal to what? It's equal to dq by dt. It's the derivative of that. Now, if you differentiate this, okay, so let's do that. If you differentiate this, how does it work out? Well, you get the Q naught there. Okay, great. There's the Q naught. That's out in front. And then you differentiate this. Now, if you differentiate this right here, what do you get? Well, what's the derivative of 1? 0. Okay. And minus, and what's the derivative of this? Well, the derivative of the exponential is the exponential back again. Okay, but we're not quite done, because yeah, it's the exponential, but then you have to use the chain rule and differentiate this with respect to t and multiply it by that. So you get this multiplied here like that, but you have to differentiate this with respect to t, and so you just get this. Okay, and now you look at this and you get, well, what do I have here? There's a minus there and a minus there, so they go away. So basically I have Q naught. I have the exponential here like this, and I have multiplied by, whoops, that like that, okay? And I can make this just look maybe a little bit nicer. The current is Q naught divided by tau, okay, multiplied by the exponential, like that, all right? Say, well, where did I get that? Well, I didn't really get it anywhere, but I mean, I did have that one little lecture where I proved this, and during that lecture, I did show this. So basically, if you have an equation for Q, for the charge as a function of time, you differentiate that, and you will get the current as a function of time, okay? And you say, but differentiating is hard. Not really. Differentiating an exponential is very easy. In fact, maybe I'll just do a quick little aside here. Let me do an aside. I'll finish off the question in a minute. But if you do like d by dt, doesn't look very good here. Let's how should I do this? I'm going to differentiate, and let me call it f of x is equal to e to the exponent x. Okay, and if I do df by dx like that, guess what it's equal to? It's equal to the exact same thing again. In other words, this is a function whose derivative is the function again. And then you go, well, but why did you get that piece in there? Well, if you have another function here, g of x like that, that's going to, and I'm going to make that equal to ax like that. If I differentiate this one, dg by dx like that, what do I get? Well, I get the same function again, but I got an a out in front like that, okay? And so that's all I did right here, all right? And so you get this equation. Now what? Well, you can just plug in Q naught, and what was Q naught again? It was one millicoulomb. All right, so you get Q naught as a millicoulomb, like this, divided by what was tau, and tau was 15 seconds, like that. And then we have the exponential, like this. And the question was after 10 seconds. So it's going to be minus 10 seconds divided by tau, which is 15 seconds, like that. And if you just plug this into your calculator and work it out, by the way, coulombs per second, that's an amp. Millicoulomb per second, that's a milliamp. So the answers are going to come up in milliamps. Let me do this very quickly on my calculator here, and I'll give you the answer. Copy, paste. And the answer is, why is it a malformed expression? Well, oh, there we go. There we go. It's equal to that, and that's in milliamps. Okay. And I might, on the test, move the decimal over 3 more and write this as 34.2. Well, what's below milli? Micro, right here, right? So if you're at milli, you go down 3 more decimals, it's going to be microamps, like that. Okay? All right, let me see if there's any questions in the chat, and then I'll do the last question. There's a couple of people watching. All right, so let me do the last problem. All right, last problem. So I had an equivalent problem like this with resistors, and the solution is actually already online. But let's do this problem with capacitors, all right? So capacitors and resistors, they're very similar when you're looking at their equivalent values, but it's kind of like the formulas kind of go the other way around. They're kind of opposite. So here, when you have capacitors in series, it's the reciprocals that add. And when you have capacitors in parallel, they just add. For resistors, it's the other way around, okay? And so they're very similar problems, but, you know, they are different because, of course, capacitors and resistors, you know, the formulas are switched around for series and parallel. Okay, so let's start answering the problem. Question number A is, what is the total capacitance of the circuit? And here I have 3 resistors. Sorry, three capacitors, okay? And what you need to do is you need to look at this thing. Let me just copy it all down here. Okay, and what you need to do is look at it and go, are there 2 capacitors here that are either purely in series or purely in parallel? Okay, and don't make the mistake of saying maybe C1 and C3 are in parallel. They're not, because C2 is in the way. Okay, so if I drew a circle, a circle around these 2, you would see that C2 is kind of like they're not really in parallel. These wires aren't joined up there. Okay, so what do? Well, you look at it and you go, oh, those 2 are in parallel, and you reduce 2 at a time. Okay, so I'm going to reduce this circuit to this circuit, and let me see if I can draw this. Oops, sorry. Yeah, I'll get it. There we go. And now this isn't C1 anymore. This is C12, and this is the way I write the equivalent, okay? So let's take a look. Here was C1, and here was C2. I'm going to take C1 and C2 out, and I'm going to replace them with their equivalent C12, like that, okay? And how do you get those? Well, they're in series, so you use this formula right here, okay? And there it is. Only, I'm not going to use C equivalent there. I'm just going to call it C12. So don't get confused by my notation here. C1 is just one of the capacitors. C2 is the other capacitor. C12 is their the combined equivalent capacitance. Okay, and so let's plug in the numbers. I've got 1 over, and this is one of those equations where if you plug in microfarads, it'll come out in microfarads. And so let me see what I have here. They're micro, but you know what? Since I'm going to put this online, let me just change the micro here to a proper symbol for micro. Here it is. And so, sorry, I'm jumping around a bit, but I can't type the micro, but I can cut and paste it, which is what I'm doing right now. All right. So what do we have here? We have C1 is a 10 microfarad, C2 is a 15 microfarad, and C3 is a 20. And so C1 is 10, and so down here we'll have 10. Actually, we don't need the microfarads. We'll just remember that the answer will come out in microfarads. So we have 10, and the other one is 15. So you have 1 over 10 divided by, plus 1 over 15, and that's going to equal, put that in my calculator, that's going to equal this number right here. Okay, that's not the answer though, because that's 1 over the answer. Okay, so you have to take the reciprocal of that number. So it's like you gotta do the reciprocals and then take the reciprocal of the added reciprocals. And what's that going to equal? That will equal 6. There we go, 6. And the answer has got to come out in, because I plugged it in microcoulombs, it's going to come out in microcoulombs. So we can actually write that into the diagram. We can say that this one is equal to 6 microcoulombs, the top one. And the bottom one, well, that one I gave you above. So let me see what I say. It was 20, okay? And so what have we done? We've effectively taken the original circuit, which had 3 capacitors, and reduced it to now just 2 capacitors. Well, we're not quite done, because I want the total capacitance. Or better word would have been total equivalent capacitance of the circuit, okay? And so we have to combine these two, and we look at them and we go, are they in series and parallel? Well, they're obviously in parallel. And so this whole circuit here is actually just going to be reduced to this circuit right here, where this guy is going to be C123. And it's not equal to 6. I don't know what it's equal to yet, but, well, actually I do, because it's kind of obvious. But that's what we're doing. So we're going to take these two in parallel and just reduce it to that one. And how do you get that one? We'll see 1, 2, 1, 2, 3. So that's the equivalent of all of them, is going to be C12, which is this one, plus C3, like that. And that's going to equal 6 plus 20, which is equal to 26 microfarads. And that's your answer. Okay? So, whoops, 26, there we go. Okay, so the answer to question A, the total equivalent capacitance of the circuit, turns out to be 26 microcoulombs. Okay, so all right, that's part A. Let's do part B. You see any questions in the chat? No? All right, so part B is, what is the total accumulated charge of the circuit? And just remember that the definition for charge is, or capacitance is Q is equal to CV, like that, okay? And you can rearrange this formula to be Q is equal to CV, like that, all right? And that's what we're going to use, okay? So if you want the total the total charge, it's just going to equal the total capacitance times V, and that's going to be 26 microfarads there, like that, multiplied by V, which is 15 volts, like that, like that. And what's that going to equal? That's going to turn out to be 390, and a farad times a volt, that's a coulomb, but we have a micro there, so it'll come out in micro coulombs, like that. Okay, so there's part B. All right, let me see here. Okay. No questions in the chat. Let me continue, and then finally the last one. So the last one's kind of hard. Well, not hard. It's got a lot of steps to it. And so I'm going to say to you, what is the voltage drop across each capacitor, and what is the charge on each capacitor? Okay. And so for this one, we have to kind of work backwards here. We got to start from this one, and then work backwards to this one, and then work backwards to this one. Okay. And let me just explain something about voltage drop, because I think this is something I've seen causes problems with students. When you have a branch in your circuit. So I know this is drawn in ASCII and it isn't perfect, but what I'm trying to draw here is this is a wire which starts from the positive 15 volts on a battery, and it goes all the way up to C1, all the way up to one of the terminals on C1. Well, here we have a branch, and it comes down here like that, and it goes all the way to there. Well, this entire piece here, this, and this entire piece here, they're all at 15 volts. Okay, the branch doesn't cause the voltage to drop. It's kind of like you're at the top of a hill, if you want to use the height analogy that I've used sometimes with voltage. This is all 15 volts up here. This is all 15 volts here. This is all 15 volts here. Oops, 15 volts here like that. Okay, and so the left-hand side of C1 is at 15 volts, and the left-hand side of C3 is also at 15 volts. Okay, now the other side of C1 and the other side of C2 there, I don't know the voltage there yet, but we will find out. Okay, and here on the other side, on the right side, you have 0 volts, and that'll be 0 volts all the way up to C2, and it's also 0 volts all the way up to the right-hand side of C3. Okay, so that's all 15 volts. Well, now we know, for instance, that for C3, on the left-hand side, you've got 15 volts, and on the right-hand side, you have 0 volts. And so you could just break this problem down a piece at a time and say, okay, well, I know that it's 15 volts across there and 15 volts across there. So let me start with this diagram. I guess, like that's the last one. So stepping back one step here like this. Okay, let me just draw that diagram here like this. Okay, and we know these values, so just not to clutter things, let me just get rid of this here. This side here is 15 volts. And this side here is 0 volts, okay? And yeah, you know what? I better put the C12 in there, otherwise it'll be confusing later, okay? So here's C12. This side is 15 volts, and that side is 0 volts. Here's C3, and this side here is, 15 volts, like that. And this side here is 0 volts, like that. All right? So we have 15 volts across them. Well, what am I asking? I'm asking for the voltage drop and the charge on each capacitor. For C3, we can already answer that. We're kind of done for C3. So the voltage drop across C3 is 15 volts. Okay. The charge on C3, you go, well, how do I answer that? Well, it's this formula here. You can apply that formula there, C is equal to Q divided by V. You can apply it over to the entire circuit, or you can apply it to a piece of the circuit at a time, okay? And so we're just going to apply C is equal to QV just to that one right there. And what am I asking for? I'm not asking for C, I'm asking for Q. So we're actually going to use just this formula right here. The charge on Q3 is, charge on C3 is this, where now you want to use like a 3 there and a 3 there. You can even put a 3 there, just meaning that it's the charge on C3, it's the capacitance of C3, and it's the voltage drop across C3. And what's that got to equal? Well, the capacitance of C3, we worked that out, and it was, what was it again? It was 20 microfarads. Actually, you didn't work that out. I gave you that one. Okay, so there we go. So there's C3. And what's the voltage drop across C3? Well, 15 to 0, it's going to be 15 volts across there like that. And so the charge accumulated on that is going to be 300 microcoulombs, like that. Okay. Remember, the total charge is going to be 390, and just C3 by itself has 300. So you know this one had better come out to be 90 microcoulombs, okay? But we'll see that in a minute, all right? So we want to do all of them. So great, we've done just C3, okay? Now, the next step is to look at C12. Before we do that, let's recognize that there's a charge on C12. And whatever that charge is on C12, it's effectively the charge on C1 and the charge on C2. Now, that may seem confusing, but what's going on there is that the charge on C2, like on that plate there, where does it come from? It comes from C1. Because C1 and C2 are in series with one another, whatever charge accumulates on C2 can only come from C1 and vice versa. And therefore, the charge on these two is the same, and the charge on those two is the same as the charge on C12. Okay, so let's just note that here. Okay, note the charge on C12 on both of them is the same as the charge on C1 and on C2 individually. And if you say why, you're wondering why, because the charge on C1 can only come from C2 and vice versa. Okay, now let me make that a little bit clearer. Imagine for a minute that there's no charge on that plate there and no charge on that plate there. If an electron were to leave C1, where would it go? It would have to go to C2. So C1 would lose an electron, C2 would gain an electron. Well, what if C1 lost 2 electrons? Where would it go? It would go to C2. So C1 loses 2 electrons and C2 gains 2. And you can see that any number of electrons that leave C1, they have to accumulate on C2. Therefore, C1 and C2 must have the same charge on it. Okay? And so let's calculate the charge on C12 because it's the same. And so we could say the voltage drop across C12 is 15 volts, okay? And the charge, so I'm just copying this to be quick about it. The charge on C12 is going to be QC12, the capacitance of C12, the voltage drop across C12, and the capacitance of C12, we calculated that above here, up above, and that was 6 microfarads, okay? So over here, this is going to be 6 microfarads. And 6 microfarads times 15 volts is going to be 90 microcoulombs. And you look at this and you go, oh, that makes sense because the total charge accumulated is 390. C3 has 300 and C12 has 90 for a total of 390. So everything is consistent, okay? So that's the charge on this. Now the voltage drop across C12, we know that's 15 volts. But at this point, we don't really need to make use of that, all right? What we want to do now is go down one more level. We want to go to this. And I'm just going to copy this piece of the circuit here like that. Actually, let me see if I can, maybe this is a better way to do it. Like that. Okay, so I don't need C3 in here. I'm just going to remove C3 because it makes life a lot easier. And now this side here is at 15 volts. Okay. Oops. Okay. I don't know what's happening here in the middle. Okay. I don't know what voltage this is in the middle. Maybe we could just write question mark voltage there. And I know that the voltage here is 0 volts, like that. Okay. So there we go. We also know one other thing. We know that the charge on C1 is the same as the charge on C2, and it's the 90 microcoulombs, okay? So this is sometimes confusing to students, but again, because the two are in series. So capacitors in series, their charges on them are going to be the same, okay? And now you look at this and you go, oh, you've got C, and you've got Q, and is there a relationship between C, Q, and you want to find V? And the answer is yes. It's this one, okay? Well, it's this one, but you need to rearrange it, okay? So the way we're going to rearrange it, I mean, so far, up to this point, let's get rid of that, up to here, that's the definition. But we want to rearrange it. What do we want to do? We want to solve for V, because we don't know the voltage drop across C1. So we want to calculate the voltage drop across C1. And if I just rearrange this equation, it's going to equal Q, V is equal to Q divided by C, like that, okay? And so we're going to use this twice. We're going to use it once for C1 and again for C2, okay? So the charge on C1, I know I'm being a little bit repetitive, but that's okay, is Q1 equals 90 microcoulombs, okay? The voltage drop across C1 is, use this equation here, okay? And this equation can be either used on individual capacitors or on the whole circuit, okay? So you know, locally or globally, all right? And now just to say, look, I'm talking only about capacitor number 1 here, like that. I'm just going to put that subscript 1. So this is the voltage drop across 1 is the charge on 1 divided by the capacitance of 1. Okay, well, what's the charge on C1. There it is, 90 microcoulombs. And what is the value of C1? I don't remember. Let me go up here. And it was 10 microfarads like this. All right. So 90 microcoulombs divided by 10 microfarads. The micros cancel. A coulomb divided by a farad is a volt. And so you get 9 volts. All right. So we know that the drop across here is 9 volts. And if you know that it's 9 volts, okay, then you know that the drop across here has to be 6 volts, all right? But let's work it out, okay? So same thing for the second one, for C2. The charge on it is also 90 microcoulombs. But now the voltage drop across C2 is V2, which is the charge on 2 divided by the capacitance of 2. And the capacitance of 2, if I'm not mistaken, was 15. Let me look above to verify that it was 15. And guess what 90 divided by 15 is? It's 6. Okay. And here's our little check. 9 volts plus 6 volts is equal to 15 volts. Ta-da! That's exactly what's happening here. So that question mark, that turns out to be 6 volts, okay, because we're at 0 here, we're at 6 volts there, and then we have to climb another 9 volts to get to the 15 volts, okay? And so that's how you do these types of problems, all right? And did we answer the full question? Well, let's see here. It said I want the voltage drop across each capacitor and the charge on each capacitor. Do we have that? Do we have the voltage drop across C3? Yep, 15 volts. And do we have the charge on C3? Yep, 300 microcoulombs. And do we have the charge on C1? Yep. And the voltage drop across C1, and same thing for C2. Okay. Could even maybe make a little chart here. I don't know. This is very useful. Okay, like C1, and then we can have like what was C1 is 90 microcoulombs, and the voltage drop was 9 volts, like this. And then we can have C2 here, and it was also 90 microcoulombs, but whoops, but 6 volts. And then for C3 we had 300 microcoulombs. We'll just move that over a bit. 300 microcoulombs. And this looks awful. Let me put some spaces in there. Put some spaces in there. And it was 15 volts across that. Okay, there we go. We've answered the question. All right, let me look in the chat, see if there's any one person watching. Okay, so I mean, this was all I wanted to do, and we're almost out of time anyhow, like 10 more minutes. But if there's any question you have, I mean, just type it in the chat. Otherwise, what I'll do is I'll just end it right here. Okay, and then I'll put this up online. All right, and this was actually part of the problems that they were like the under electricity, they were the extra problems. And under the solutions, I solved number 3, but I didn't have the solutions for 1, 2, and 4, I think, yeah. And so these are the solutions, all right? So any questions? Otherwise, going. All right, bye-bye. End of the stream.